perform the operations like controlling the 8085 processing. Whatever the microprocessor, the 8085, it's performing the various type of operations like arithmetic operations, logical operations, and like memory read, memory write. So all the operations, how they are controlling, if the microprocessor want to control its processing, then we use these instructions. Now the first instruction which come under this category, it is NOP. This instruction means no operation. There is no operand in this. We only write NOP in the program, and this instruction means that no operation is being performed by the 8085 microprocessor. The microprocessor will stop its all the operations and it will remain there in that state, whatever task it is performing. So this instruction NOP, it means that no operation is performed by the microprocessor. The instruction is fetched and it is decoded. This instruction NOP and the next instruction written to it, it is fetched and decoded, but not executed. Whenever any instruction is written in the microprocessor, then first thing whatever the microprocessor does is to fetch that instruction, then decode it, and then execute it. So these are the three operations performed by the microprocessor. This is how it works on an instruction. First, it fetch the instruction, then decode the instruction, and then execute that instruction. So when this instruction NOP is written in the program, then microprocessor will fetch that instruction, decode that instruction, but it will not execute that instruction. Okay, so the microprocessor, it's stopping its operation at this position. So it comes under the control instructions category because it is controlling the processing of the or the working of the microprocessor. So this was the first instruction, NOP, that means no operation. Now second instruction. So next instruction under the control instructions category is HLT. This instruction means halt, and enter wait state. The full form of HLT is halt, that is to wait, stop at this position and enter into the wait state condition. So what this instruction means, the CPU, the central processing unit of the microprocessor which performs all the processing, that finishes the executing the current instruction. Whatever instruction the microprocessor is currently executing, it will finish the execution of that instruction and halts any further execution. It will stop. Halts means it will stop any further execution of the instruction which is written after HLT. And an interrupt or reset is necessary to exit from the halt state. Now, after halt state, if HLT is written in the program, then the microprocessor, it will stop the execution of any further instruction which is written after HLT. And if we want to reset or bring the microprocessor into its initial condition so that another program or any other instruction can be executed by the microprocessor, then we have to either give an interrupt to the microprocessor or we have to reset the microprocessor chip. So if it comes to its again to its initial condition, then any further execution of the instruction can be done after this HLT instruction. Now, what's the difference between HLT and NOP? NOP, we have studied that it is no operation, and this instruction NOP, it is what? It is stopping the execution of any instruction. If NOP is written, then that instruction will be fetched, decoded, but it will not be executed. But if HLT is written, then the instruction will be executed, but further any execution of any instruction, it will be stopped. So there is the difference between NOP and HLT. NOP does not allow the execution of instruction, but HLT allows the execution of the current instruction but stop the execution of any further instruction. Okay, so there is a difference between NOP and HLT. Now, next instruction under the control instructions category is DI. This means disable interrupts. This instruction also has no operand in it, only DI is written in the program, and this means to disable the interrupts. So what the microprocessor does, if any interrupt is being given to the microprocessor, then it will disable all the interrupts. Okay, no execution, or if there is any call instruction related to the interrupts, then no execution of the interrupts will be done if DI is written there. So this instruction disable interrupts, it is doing that when it is written in the program, then the interrupt enable flip flop, it is reset, that is it comes to its initial condition, its value becomes 0. So this interrupt enable flip flop is reset, and all the interrupts which are given to the microprocessor, they are disabled. None of the interrupt will be executed except trap, because trap, it is the non-maskable interrupt having the highest priority. So if trap is being given to the microprocessor, then this instruction, it will not disable this trap interrupt, it will be executed. But any other interrupt except this trap, if it is given to the microprocessor, then it will be disabled due to this DI instruction. And also the interrupt enable flip flop, its value becomes 0, it is in the reset position. And no other no flags are affected due to this instruction. Their value remains the same. If they are set, then it will remain in the set position. If they are reset, then they will remain in the reset position. So this instruction is basically disabling the interrupts. It is used in the interrupt operation. Next instruction is EI, that is enable interrupts. Now, if we have disabled the interrupts and if we want to enable them again, then we can use this instruction EI. So this instruction enable interrupts. So this instruction EI, that is enable interrupts, it is enabling this interrupt enable flip flop. It is set, that is it is enabling all the interrupts. All the interrupts will be executed in the 8085. That means all interrupts they are enabled and no flags are affected due to this instruction. Now if we want how the microprocessor, it will come to its initial condition, reset condition. If the system is reset, after the system is being reset and the acknowledgement of an interrupt, because this instruction it is enabling all the interrupts. So if we are having INTR, interrupt request is there, and then we have RST 027, any of the instruction is interrupt is there, trap is there, then all the interrupts which are being given to the microprocessor, all the interrupts will be executed. And after the acknowledgement of all the interrupts, then the interrupt enable flip flop, it is again reset, because this instruction it is setting the flip flop. Now after the all the interrupts they are being executed, they are being acknowledged by the microprocessor, then the flip flop it will be again reset. And if the system is being reset, then also the flip flop will come to its reset condition, and then all the interrupts will be disabled. If we want to again enable the interrupt, then again we have to write the EI instruction in the program. If first time we have given EI, then it will execute all the interrupts, it will acknowledge all the interrupts, and then change the enable flip-flop to its reset condition. If again you want to enable all the interrupts, then again you have to write EI, and then the interrupts which you give after that, then those interrupts will be executed. Okay, and if you have given if the system is reset also, then also the flip flop will be in the reset condition. So this was enable interrupts. DI and EI, they are used in the interrupt functioning of the 8085. Now next instruction is RIM and SIM. This instruction RIM, its full form is read, interrupt, mask. This instruction, it is a multi-purpose instruction, multitasking. It is doing various types of tasks. First, let us see that what its 8 bits they are defining. So the 8 bits of this instruction RIM, they are defining the various interrupts. It is giving us the status of the, to read the status of the 3 interrupts, RST 7.5, 6.5 and 5.5, and also it defines the serial data, serial input data bit. It is also defined through this instruction. So we can say that this instruction, it is a multi-purpose instruction. And it is used to read the status of the 3 interrupts, RST 7.5, 6.5 and 5.5. and also to define the serial input data bit. Now what it is doing, the 8 bits, they are loaded in the accumulator with the following interpretations. If there are 8 bits in the accumulator, then how those 8 bits they are defined through this instruction RIM. The D naught, that is the least significant bit, it is for the RST 5.5 interrupt. D1 is for RST 6.5 and D2 is for the RST 7.5. Now what these 3 bits they are defining, that the interrupt will be masked if the bit is equals to 1. Now if the value of this D2 bit is 1, then the interrupt RST 7.5, it will be masked because these are the maskable interrupt. So that interrupt will be masked. Masked means at that time the 8085 it is not going to execute or acknowledge this interrupt. It is not going to bother that this interrupt RST 7.5 is present there. First it will execute other interrupts or execute other instructions, and this interrupt will be masked. It will not be executed by the 8085. If 6.5 is 1, then if this bit D1 is 1, then 6.5 will be masked. If D0 is 1, then 5.5 will be masked. So these 3 bits, they are defining that whether the interrupt will be masked or unmasked. Now this D3 bit, this is IE, that is the interrupt enable flip-flop. It is set if bit is equals to 1. So this is for setting or resetting the interrupt enable flip-flop. If it is 0, then it will be reset. If it is 1, then the flip-flop will be set. That is, all the interrupts will be enabled. So this is used to enable or disable the interrupts present in the microprocessor. Then we have D6, D5 and D4. These 3 bits, they are for setting that the interrupts are pending. If there is any interrupt which is pending in the microprocessor, then that corresponding bit will be equals to 1. Pending means there are priorities in the interrupts. We have the priorities are defined that if 4 or 5 interrupts are present at the same time, then which interrupt will be executed first, which will be second, which will be third, and which will have least priority last, that interrupt will be executed. So the priorities will be defined. If the microprocessor is executing the first interrupt, then these 3 bits they will show that this interrupt is pending. Microprocessor has to execute this interrupt also. So these 3 bits they are for defining that whether any interrupt is pending. If it is 1, it means there is a pending interrupt in the microprocessor. The D7, that is the most significant bit, it will define the serial input data bit. When the microprocessor it is performing the serial data communication, it means it is being interfaced with the peripheral device, and there is an input and output data bit there. The bit which is coming, if it is 0, it means 0 bit is coming to the microprocessor. If it is 1, it means the 1 bit is coming to the microprocessor. Means the data, that whether it is 0 and 1, it will be defined by this bit. Okay. So this read interrupt mask RIM instruction, it is defining the 8 bits of the accumulator, whatever the 8 bits, because accumulator is an 8-bit register, so it will have an 8-bit data, and those 8 bits they will define by they are defined by this RIM instruction, that the most significant bit it will be taken as the serial input data bit. Then D7, D6, D5, D4 they will be taken as the interrupt pending bit. Then D3 will be taken as interrupt enable flip-flop bit, and D2, D1, D0 are the interrupt masking bits. So this is the RIM instruction. The next instruction is SIM. It means set interrupt mask. This instruction also has no operand. And it also specifies the 8 bits of the accumulator. If this instruction sim is written, so the 8 bits of the accumulator, they will be interpreted according to this sim instruction. So this is also a multi-purpose instruction. This instruction is used to implement the 8085 interrupts. The three interrupts are ST 7.5, 6.5 and 5.5, and it is also used for the serial data output. Now how the 8 bits they are defined, let's see. So the 8 bits of the accumulator, they are defined by this sim instruction like this. The most significant bit D7, it is the serial output data. When the microprocessor it is performing serial data communication, then the bits will be input and output from the microprocessor. Now if this bit is 1, then 1 is as an output bit to the other peripheral device, and if it is 0, then 0 is the number which will be output as a output bit to the other peripheral device. So this is defining the output bit 1 or 0. Then we have SDE, that is serial data enable. The serial data communication, there will be a flip-flop, and if it is 1, then that serial data communication will be enabled, it will be performed. If it is 0, then that communication will be disabled. So serial data communication, it is enabled and disabled through this bit. If it is 1, then it will be enabled. If it is 0, then it will be disabled. Then we have D5, these are the don't care bits. If it is 0, if it is 1, then it doesn't it has no effect on the any operation. So these are the don't care bits. If it is written X, then it means there is whether it is 1, it is 0, there will be no effect on the operation of the microprocessor. Then we have D4 R7.5, that is reset this interrupt RST 7.5 if this bit is 1. If it is 1, then this interrupt RST 7.5, it will be reset, that it is its value becomes 0. The microprocessor, the interrupt will come into its initial conditions. Then we have MSE, this is mask set enable. M for mask, S for set and E for enable. So this is, if this bit is 1, then these bits D2, D1, D0, they will come into effect. If it is 0, then these bits, it will not come into effect, there will be no operation performed due to this bit. So this D2, D1, D0, it is they are used for masking the interrupts RST 7.5, 6.5 and 5.5. If D0 is 1, then 5.5 will be masked. If 6.5, this bit D1 is 0, then 6.51 will be masked. If 1, then 7.5 will be masked. So if these bits, any of these bits is set that it is value is equal to 1, so correspondingly that interrupt will be masked. So these three bits are used to mask the three interrupts 7.5, 6.5 and 5.5. Now this bit, if this bit is 1 and any of these bits, suppose this D1 is 1, then 6.5 will be masked. If this bit is 0 and this 6.5 is 1, then no operation will be performed because this bit is 0. This bit has to be 1 if masking operation has to be performed. That is why this bit is known as mask set enable. Okay, if it is 1, then only this masking operation will be performed. If it is 0, then no operation will be performed, no masking will be done. Okay, so this was sim instruction, that is setting the interrupt masking, because what this instruction is doing, it is masking the interrupts. That is why it is sim, S for set, I for interrupt and M for mask. So read interrupt mask and set interrupt mask, they are used in the interrupt operation of the 8085. So these instructions, they are used for controlling the operation of the microprocessor. NOP, no operation, HLT, halt, and then we studied DI and EI, that is to disable and enable the interrupts, then SIM and RIM instructions. So these were control instructions. So all the instructions in the instruction set of 8085 we have studied here, and we have divided into them into 5 categories: arithmetic operations, then arithmetic instructions, then logical instructions, then control instructions, and branching instructions. So we have studied all the instructions of the this 8085, and I hope that you have understood all the instructions very well. Thank you.